in this video, we will do some examples involving the Gini Index. Okay, so I want to begin with example 2. And again, remember that my numbering continues the numbering from examples in previous videos. So in an earlier video, I did example 1, and this is example 2. So in this example, let's find the Gini Index for the Lorenz curve, f of x equals 1 over 20 x plus 19 over 20 x to the 9. And we saw this Lorenz curve in a previous video of this section. It was for US wealth. Okay, so let's remember our formula for the Gini Index. So I'm going to call the Gini Index G, and the formula is we take 2 and you multiply 2 by the integral from 0 to 1 of the curve of perfect equity equation, which is x, minus our Lorenz curve. Okay, so our Lorenz curve, got to put in parentheses, 1 over 20 x plus 19 over 20 x to the 9. So this whole thing in parentheses, this was f of x. And I need the parentheses around it so I don't forget that I need to distribute this negative sign. And in fact, in the next step, let's distribute that negative sign. So we get g equals 2 times the integral from 0 to 1. So if we distribute that negative sign, we can combine this x and the minus 1 over 20x. So you can combine these terms by getting a common denominator. And if we do that, we'll get 19 over 20 x, and then we'll get minus 19 over 20 x to the 9 dx. And to make my arithmetic a little bit easier, I'm going to go ahead and factor out this 19 over 20. So we'll get 2 times 19 over 20 factored times the integral from 0 to 1, x minus x to the 9. And from here, it's not too bad. It's just a basic integral. So with the 2 times 19 over 20, that simplifies to 19 over 10, because I can cancel a 2. And then the antiderivative of this is x squared over 2. Well, let's write that better. X squared over 2 minus x to the 10 over 10. And then I need to plug in 1 and 0 into this. Okay, so the 19 over 10 stays factored out. And then that's going to end up multiplying. Now when I plug in 1, I get 1/2 minus 1/10 minus what I get when you plug in 0. And if you plug 0 into both of these terms, you'll get 0. So we'll have 0 and then minus 0. It's awesome. And if we simplify this, we get 19 over 10 times, with the 1/2 minus a 1/10, getting a common denominator, we will get 4 over 10. And then this becomes, if you multiply it out, this is, top is 76, bottom is 100, and writing that as a decimal is 0.76. That is our Gini Index here. So this is closer to 1 than it is to 0, which means it tends more towards being unequal. All right, let's look at another example. Okay, in this example, it says that 46% of SCU's budget for employee salaries goes to just 8% of its top administrators. Assume a Lorenz curve of the form f of x equals x to the p. So p is some unknown number here. And in part A, I want to find what p is and round our answer to 2 decimal places. Okay. So we know that Lorenz curves tell us some information about like a percentile of the population and then how much of a resource that they have. And the part of this statement that tells us about percentage of a population and percentage of a resource is this first part. Okay, so I'm going to focus on that and sort of carry this down over here. And I need to somehow translate this to math. So the way I can do that with the Lorenz curve type thing is, I got to keep in mind that we need to be able to formulate a sentence like, the bottom something percent of my population get some percent of the resource. So this first blank refers to the population. The bottom what percent of the population get what percent of the resource. All right, so I want you to pause the video for 1 minute to see if you can fill out the numbers that go in these blanks. This is a good check to see, do you conceptually start to understand how these numbers will factor into a statement like this? 4, 3, 2, 1, pause that video. Pause it for a minute to think this through and see if you can fill in those blanks. All right, so let's talk about it together. Let's first identify what the population is here. So the population it's talking about is employees, SCU employees. And what is the resource that it's talking about? Let's put this in a different color. So the resource is salaries, or maybe more specifically, it's the budget that SCU has for salaries. Okay, so I need to describe the bottom what percent of the population first. So it's talking about the top 8% of administrators and them earning a lot of money. So top 8% corresponds to bottom 92%. So it's really important that you understand where I got that from, because top 8% means we're talking about bottom 92%. Okay, and the bottom 92% would get how much of the resource? Well, if the top 8% got 46% of the budget, that means the other part, the bottom 92, would get 54%. They would get 54%. Because this is coming from, this is 100 minus 8. And the 54 is coming from 100 minus 46. All right, so I should be able to convert this now to a statement that looks like f of something equals something. So the bottom, whatever percentage of the population, goes inside the parentheses. I convert it to a decimal, and it becomes 0.92. And how much of the resource they get is the output. So 54%, convert that to a decimal, and I get 0.54. Okay, so that analysis, how we reason this out, converted it to a math statement, and then use that to plug into what the Lorenz curve input and output should be, that was essential to this question. So definitely make sure and you review this if you had questions about how we work this out. And ask questions if it still doesn't make sense. All right, so what I'm going to do now is 0.92, let's plug it into this formula for f of x. And we'll get 0.92 to the p power. And that needs to be equal to 0.54. And now I need to solve this equation. So now we got to solve this equation. And for this, when I have a variable like this in the exponent, often we can use logs to solve this. So I'm going to take ln of both sides. ln of 0.92 to the p equals ln of 0.54. And now I'm about to use a log rule. Because remember, ln is just a special type of log. ln means log base e. Okay, so there's a log rule that says if you have a power like this inside of a log, you can pull it to the front. So the p can come in front, and then you'll have ln of 0.92 equals ln of 0.54. And now we just isolate for p by dividing the ln of 0.92. So p is ln of 0.54 over ln of 0.92. And the question said let's round to 2 decimal places. So if I use a calculator for this, we end up getting about 7.39. And I'm going to box the whole thing, because I could definitely ask you to do something like this and leave your answer in a form without a calculator, in which case I'd ask you to leave it in the previous fractional form. Okay, so let's do another part to this example. So B, now let's find the Gini index. So find the Gini index. Alrighty, so let's use our formula for the Gini index. G equals 2 times the integral from 0 to 1, x minus our Lorenz curve. And our Lorenz curve here it has the form x to the p, and now we're going to use the number 7.39 for our p value. That's what we got p was. Okay, dx. Alrighty, so now let's do this antiderivative. So one thing I'm going to do is I'm going to take this 2, I'm actually going to distribute it in, which might look a little bit weird, like why am I doing that? But the reason I'm doing that is because if I do that to the first term, 2x has a really nice antiderivative. It's just x squared. And I noticed that And that just made my computation a little bit easier. And with the next term, if I do a reverse power rule, the 2 would be there, but then we'd have x to the 8.39 when you add 1 to that power, and then you divide by that new power, 8.39. Okay, and then vertical line to indicate I need to plug in 1 and plug in 0. If you plug 1 into this, you get 1 squared, which is 1, and then minus 2 over 8.39 minus what we get when you plug in 0. But with both of these terms, when we plug in 0, we just get 0. So that's kind of nice. And I'm going to round this to 2 decimal places as well. This ends up being 0.76. All right, so that is my Gini index. And it's actually just a complete coincidence that I got the same Gini index here as I did in the last example. In general, the Gini indexes are not necessarily going to be the same. All right, so let's do one more part of this example. Part C, how much of salary budget, goes to the top earning 2% of SCU employees? Alrighty, so for this one, I want to give you all a chance to try this, but more time. So this time, pause the video for about 2 to 3, there we go, 2 to 3 minutes to try this one. 4, 3, 2, 1, pause the video. Pause the video for about 2 to 3 minutes to try this. This one's slightly more conceptual in nature than the previous question, so I definitely encourage you to seize this time to try this question. Believe that the time that you put in during these pauses is helpful. Even if you don't quite make it to the end, it's an opportunity for you to assess how well you know this material. And even if you're not able to finish, which is totally fine, I don't necessarily expect you would be able to in 2 to 3 minutes, how well you can start to break down what are the key ideas to begin the question. All right, so hopefully you did that. Hopefully paused it for about 2 to 3 minutes. So just like part A, I'm going to need to convert this statement about percentages to a statement like the bottom something percent get something. Get something. So in this question, it's talking about the top earning 2% of SCU employees. So I need to convert that to a statement about the bottom whatever percent. So the complement of top 2% would be bottom 98%. That's sort of the other sort of opposite part to it. So how do I determine how much the bottom 98% gets? Well, what I do is, at this point I know my Lorenz curve completely. They would get what I get, f of 0.98. I sort of have to plug 0.98 into my Lorenz function and see what that output is. Okay, so if I do this, this is going to be approximately equal to, so I plug 0.98 in, and then this is to the p power, and p was about 7.39, and that's why I'm putting approximately equal to, because p was approximately 7.39. Okay, and this is approximately equal to 0.86131. And if I were to think about this as a percentage, this is about 86.13%. Technically, I can say 131%. So, and what is that referring to? The resource here was the budget, the salary budget of the budget. Salary budget, technically. Okay, so now we know how much of the salary budget the bottom 98% of employees get. So we got to answer the question. So thus, the top 2% would get the whole amount. I'm going to do it in decimals first. 1 minus 0.8631 equals 0.138. Whoops, sorry. That should be 13. Whoops, I just miswrote this. This should have been 86, not 31. It should have been 8613. So when I subtract them, I should get 0.1387, which as a percentage is 13.87%. So they get that much of the salary budget. Salary budget. So why did I do 1 minus this decimal? is because if you think about it as percentages, we are doing 100% minus this 86.13%. And that's how we got this. All right, so I'm going to box this. This was our answer. So in terms of our goals for this section, we have finished our second and last goal, which is we've discussed, let's put that in red. We've defined what the Gini Index is and how it's connected to measuring how equally or unequally a resource is distributed. And we did some examples.